We conclude our study of first-order differential equations by looking at a nonlinear model. Now, if P of t denotes the size of a population at time t, the model for the exponential growth will begin with the assumption that dp dt is equal to kp for some k greater than 0. In this model, the growth rate is defined by 1 over p dp dt. And this is a constant. Specifically, this is the constant, k. Now, true cases of exponential growth over long periods of time are very difficult to find because the limited resources of the environment will at some time exert a restriction on the growth of a population. The assumption that the rate of a population grows or decreases is dependent only on the number p present and not on any time-dependent mechanisms such as seasonal phenomena can be stated as dp dt is equal to p times f of p, where f is some function. This is called the density dependent hypothesis. Now, let's suppose that an environment is capable of sustaining no more than a fixed number k of individuals in a population. This k is called the carrying capacity of the environment. So for this function f up here, we must have f of k is equal to 0. We will also define f of 0 to be some value r. Now, the simplest assumption we can make about f is that it's linear. That is, f of p is equal to some constant c1 times p plus another constant c2. Using these conditions, we'll get f of 0, which is r, has to be c1 times 0 plus c2, which is just c2. And so we find that c2 is the constant r. Now we also get f of k, which is 0. So this will be c1 times k plus r. And if you solve this for c1, we find that c1 is negative r over k. And so our function becomes f of p is equal to r minus r over k p. And so our new differential equation becomes dp dt is equal to p times r minus r over k times p. We're going to relabel constants. We're going to say, well, let a be defined as r, and we'll let b be defined as r over k. And so we can now rewrite this differential equation. Dp dt is equal to p times a minus b p. This is called the logistic equation. The solution of this is the logistic function, which we will look at shortly. Now we can rewrite the logistic equation as dp dt equal to ap minus bp squared. And we take a greater than 0 and b greater than 0. Now this non-linear term right here, this minus bp squared, can be interpreted as an inhibition or competition term. Furthermore, in most cases, A will be much greater than B. We are now going to find the logistic function. So we have dp dt is equal to AP minus BP squared. We're going to solve this using separation of variables. So we're going to write now dP over AP minus BP squared is simply equal to dt. Decompose the left-hand side into partial fractions. We're going to get 1 over AP minus BP squared is equal to 1 over P times A minus BP, which is equal to alpha over P plus beta over A minus BP. So this whole thing will mean that 1 is equal to alpha times A minus BP plus beta times P. If we let P equal 0, we'll get that 1 is equal to alpha times A, which means that alpha is 1 over A. If we now let P be A over B, we'll get 1 is equal to beta times A over B, and so beta would have to be B over A. So this equation now becomes one over a times 1 over p plus b over a times 1 over a minus bp dp equals dt. So we're going to go and integrate. So we're going to get 1 over a times the integral of dp over p plus b over a times the integral dp over a minus bp is equal to the integral of simply dt. This now gives 1 over a times the log of p minus 1 over a times the log of a minus bp is equal to t plus some constant. We now wish to solve for p. Well, the left-hand side can be combined, so we get 1 over a times the log of p over a minus bp. This is now equal to t plus c. Multiplying both sides by a, log of p over a minus bp is equal to at plus, still a constant. A is, remember, a constant value. Which means that p over a minus bp is equal to c, a constant, e to the at. This means that p is equal to ca e to the at minus bc p e to the at. Isolating p on the left-hand side, we'll get p plus bc p e to the at is equal to ca e to the at. Therefore, we find that p of t is equal to ca e to the at all over 1 plus bc e to the at. Simplifying this, we can write this as ac over bc plus e to the minus at. Now, if p of 0 is equal to some value p naught that is not a over b, then we can find the c. So we get p of 0, which is equal to p naught, is ac over bc plus e to the 0, which is 1. This means that bc p naught plus p naught is equal to ac. Now again, we want to isolate c on one side. So we're going to get that p naught is equal to AC minus BC P naught. And this gives us that C is P naught over A minus B P naught. We now need to plug this C value in up here. So P of T is equal to A times P naught over A minus B P naught. And that whole thing is over B times P naught over A minus B P naught plus e to the minus AT. So we get A P naught over A minus B P naught all over B P naught plus e to the minus AT times A minus B P naught all over A minus B P naught, and these denominators will cancel. And we get P of T is equal to A P naught all over B P naught plus A minus B P naught e to the negative AT. This is our logistic function. Suppose a student carrying a flu virus returns to an isolated college campus of 1,000 students. If it is assumed that the rate at which the virus spreads is proportional not only to the number X of infected students, but also to the number of students not infected, determine the number of infected students after 6 days if it is further observed that after 4 days, X of 4 equals 50. We're going to make a further assumption. We're going to assume that nobody leaves the campus throughout the duration of this disease. So we set up our initial value problem. Dx dt is equal to kx times 1,000 minus x, right? Because it tells us that it's proportional not only to the number infected, which is x, but also to the number not infected. Well, if x is infected, then there's 1,000 minus x not infected. And we have the initial condition x of 0 equals 1. So we now wish to solve this. So we're going to rewrite it. Dx dt is equal to x times 1,000k minus kx. And again, x of 0 is equal to 1. Well, here we can now notice that A is 1,000k, B is k. So our logistic equation, which we've already derived, we get x of t is equal to A times x of 0 over b times x of 0 plus a minus b times x of 0 e to the negative at. Now just plug in all of our values. So we get 1000k over k plus 999k e to the negative 1000 kt. Well, all these k's will wind up dropping out. So this becomes 1000 over 1 plus 999 e to the negative 1000 kt. We now need to find this k value. Well, to do this, we're going to make use of the fact that x of 4 is 50. So we're going to get that 50 times this 1 plus 999 e to the negative kt is equal to 1000. I'm sorry, this t is of course 4. So this is negative 4000k. If we divide by 50, we're going to get 1 plus 999 e to the negative 4000k is equal to 20, which means that 999 e to the negative 4000k is equal to 19. Which means that e to the negative 4000k is equal to 19 over 999. Negative 4000k is thus the log of 19 over 999, which means that k is negative log of 19 over 999 all over 4000. Therefore, our logistic function is 1000 over 1 plus 999 e to the negative, not negative, sorry, to the 1/4 log of 19 over 999 times t. We can now go about solving our problem, which was we wanted to find x of 6. So this is 1000 over 1 plus 999 e to the 1/4 log 19 over 999 times 6 And this will wind up giving about 276 students. So after 6 days, there will be about 276 students infected. This concludes our lesson on the logistic function. I hope you have learned something, and we will see you in the next one.